we'll be writing a Python code to generate Mandelbrot set. The algorithm can be found on this website, and there are codes written on this website. I refer those codes as well. The code and the basic algorithm is quite simple. So we start with a complex number, a point in a complex plane C, and we use this recurrence, this iteratively find Z, and using this formula Z square plus C, and we look the starting value, the seed value 0, and we look if the series generated is converging or it is just bulges up, and accordingly we say that if it is bulging up, we don't take that point, otherwise we take the point as the Mandelbrot, one of the points in the set. And the conditions for the unbound orbits is the modulus of Z is greater than 2, and we discard those points. So first we import NumPy. Also we need the plotting library, matplotlib. Import pyplot as plt. We'll be using that to visualize we'll use that to visualize the image that we draw. And so we start with an image, the x dimensions say 400, image y dimension to be 300, and so we have generate on this image, we break down them into say 400 pixels along the x and 300 pixels along the y axis. So we can generate a mesh along the x axis with a NumPy. So we use NumPy space. So we took the starting point as these are the values. This is the region in the xy plane or the complex plane that will look from -2.5 to 1.5 in the complex plane, and the step value, which is given by num for the lint space or the line space, is we want 400 points, so we take 400 plus 1, and same thing, we generate a mesh along the y-axis. Is this basically it breaks that region into, and we plot from say 1.5 to plus 1.5, and the num is given, we break the y into 300, so we 300 plus 1, so that we get 300 pixels. So this mathematical region, the xy plane or the complex plane, we break that into these points, and basically we have a map from here to the image, which will be represented by as pixels with x and y, says 0, 0 on the top left corner, and 0 1 0 2, like, you know, it goes up x-axis and the y to the down on the downward direction. So now we have now we initialize our image as, so we generate the image as the zeros, the numpy, and the shape value will be length of y. So, and we can need one more brace. What's happening? Yeah, so this generates an image of the size of this mesh here, and depending upon the length, so we have 400 and 300 points, 400 points along the x and 300 points along the y direction. So we could look that image now using from the py plot image show and just check what we get. If you run it, so I have an error. So I need to check what I'm doing. NumPy as np. Yeah, I have an error, so this is linspace. So let's see. Yeah, so we get this image. So we need to, this is not what I want. So this is what we want, I believe. Yes. So we have 400 points along the y and 300 points along, sorry, 400 points along the x and 300 points along the y direction. So now we don't need to keep looking at it, so I can just I'm gonna comment that out. Okay, so now we start with our, we keep choosing, say we have this mesh x here, so we pick up this top left, start from the first point, pick up 1 point from the y, and we keep moving along the x direction. So what we do, we start a loop. So for y in mesh y and for x in mesh x, so we get 2 points. And now so we initialize, we pick up a random point, pick up a point, pick up this y, x, y point and assign to the complex values, the real part of the complex number as x. We could do cr, c imaginary as x, y, and the seed value for the z is zr comma zi is 0. And so now we need to iteratively find that equation that we seen here, this one. We need to keep doing this. So we use a counter. We have another loop, so we generate a counter, count equal to 0, and so the idea is so on the image, so we will put, say, we generate a color code so that we can choose the points that we want and the points we don't want. We choose the points which lie inside the Mandelbrot set as black. That is just the key at the moment, so that we can know which points is inside and which points we have to discard. And we start our code, say 50 iterations. We go 50 iterations and check if the Z is bulging up. And of course the count plus 1. So count will be equal to 1 in the first iteration. And now we calculate the modulus, Z modulus square, rather than calculating the square root to check the divergence or the convergence conditions. We do these conditions here. So we say modulus square is greater than 4. So we say 0 times real plus imaginary. So if that one is our modulus square, and then we check if Z mod square greater than 4 means we don't want that point. So we have just put the keyword, the points we don't want, take 0% as white. So now just check for the time being, is everything okay? Yeah, I just put, I'll change it later. Time being, just put it couple of them. Yeah, so now and so the moment we have a point, the moment the modulus is greater than 4, which is the condition for the unbound orbits, so we just break the loop. We don't want to carry on anymore. And then we find what we need to find is so Z equal to Z square plus C, so which basically will come something like, on the left hand side we have Z R plus the imaginary Zi equal to, on the right side we will have Z is real C square minus C imaginary square, and there will be 2 times ZR ZI and again an imaginary part, plus on we have the C real part plus the imaginary CI. So we can pack that equation, and so we get basically the recurrence formula will be if you separate the real and imaginary parts, so we get basically ZR and then we have minus ZI and we have plus the real part of this, comma, and then, so if you want, we could put this in parentheses, and 2 star 2 times we have zr zi plus the imaginary part. This is the imaginary part. Alright, so that's so update this. Now this so this is z square, so this goes back, and then the loop continues and checking this condition if it is bound or not here, the while loop. And so let me run that. So right at the moment I don't know if there's any. So now we come out. So the idea is, if our color is white, so if it is if we have a bound, if we have a point which is outside, in that case, so we represent, which means basically we have broken out of that particular loop. We say image I j there's a mistake. So what we do is of course, if it is unbound, not bound, if it is unbound, we initialize that to be 1. So now we have the image, the points, the indices corresponding to so we have initialized the whole thing as white. All the values inside the image were 0, 0, 0, all zeros. Now whenever we have a bound, we represent it by 1, which would be, say, the opposite color or a different color. So now if we run, say, yeah, so of course I need to each point is I comma j, so I have to define that I and j. So we start from set of y, I comma y, so we enumerate it, so which basically will pick up the zeros. So I will be 0 and the y value, 1 and the y value, and similarly for here j. So we have for corresponding x and y, we have the 0, 0, the corresponding image values. And let's see, yeah, so we have getting the image. So we can increase the value and check what happens. Yeah, so we have the Mandelbrot set, and so this is it. We could, of course, make it, we can draw it in a different way, like more, if you are a little bit more artistic, it looks more like an art, So what we have to do for that, we could play around with we can the whenever it is not the unbound, we can put a color value depending upon our calendar. For example, if I say that image I j equal to count, so let's see what we get. We have this beautiful pattern. I really love that one. Or we could also say, make it a bit more. We could say image assign function image ij equal to, so some import math dot sign of count, that may be small, so you multiply by some number and then integer value, and let's see if it is alright. So that one is really beautiful. And we could of course use monochrome here and say that the C map value equal to, say, PLT. From PLT we can use the CM binary and then look at the same thing. Yes, so it's also beautiful. So this is basically the code, and you could also save it. So that's it. You could leave any comments in the comment section. I'll answer it. I'll get back to you. Thank you for watching. Enjoy coding. Bye.